Flying at Mach 6 means traveling 6 times the speed of sound. At these velocities, standard jet engines fail. To pierce this hypersonic frontier, engineers had to design an engine with 0 moving parts. Traditional commercial airplanes use turbofans. They contain rows of spinning fan blades that physically squeeze the incoming air, mix it with fuel, and burn it to create thrust. Mechanical compressors act like paddling a bicycle uphill. Your legs, the compressor blades, do all the physical work to squeeze the incoming air to prepare it for combustion. But if you try to fly faster than Mach 2.5, the air entering the engine becomes so hot from friction and compression that the spinning metal blades will warp and melt. A ramjet removes all moving parts. As the aircraft flies supersonic, the engine rams the incoming air into a narrow passage, slowing it to subsonic speed, which compresses and heats it. Imagine holding a funnel out of a fast-moving car window. The wind rushes into the wide opening and is forced into the small neck, compressing itself without any mechanical fan. This is passive compression. Once you cross Mach 5, slowing the supersonic air down to subsonic speeds inside the engine generates too much friction. The air temperature rises so high that the engine will melt. A scramjet or supersonic combustion ramjet solves this. Instead of slowing the incoming air down, the air flows through the entire engine at supersonic speeds, and the fuel is burned directly in this stream. Lighting fuel in a supersonic airstream is incredibly difficult. It is the fluid dynamics equivalent of lighting a match inside a Category 5 hurricane and keeping it lit. Since scramjets have no compressor blades, they must squeeze air using fluid dynamics. When traveling at hypersonic speeds, the air piles up and forms sharp-angle pressure waves called oblique shock waves. It is like a snowplow pushing snow. The angled blade of the plow forces the snow to pile up and compress into a dense block. The angled inlet walls of the scramjet act as the plow, compressing the air. The supersonic air bounces off the angled walls inside the inlet. With each bounce, the air becomes denser and hotter, preparing it for combustion without any mechanical parts. When fuel burns inside the combustion chamber, it creates a massive pressure spike. This high pressure naturally wants to expand in all directions, including pushing backward out of the front of the engine. If this back pressure pushes the shockwaves out of the inlet, it disrupts the incoming supersonic airflow, causing the engine to choke. This event is called an unstart and can tear the vehicle apart. To prevent this, engineers install an isolator, a straight channel between the inlet and the combustor. The isolator contains a shock train of small shockwaves that absorbs the pressure feedback. The isolator acts like a hydraulic shock absorber or a double-door airlock. It prevents the violent pressure spikes in the combustion chamber from escaping out the front door, keeping the engine running. At Mach 6, air travels through the combustor at up to 3 miles per second. This means the air molecules are inside the chamber for less than 1 millisecond, requiring near-instant mixing. Imagine trying to pour a packet of sugar into a rushing fire hose and expecting every single grain of sugar to dissolve and mix perfectly before the water exits the nozzle. That is supersonic mixing. To solve this, scramjets use strut injectors, aerodynamic wedges that extend into the airstream. They inject fuel directly into the core flow and act as anchors to keep the flame burning. Scramjets also use vortex generators. These tiny ramp-like structures on the combustor walls create miniature tornadoes that fold the fuel and air together, rapidly increasing the contact surface area. Engineers also use shock turbulence interaction, intentionally bouncing weak shockwaves off the fuel spray. The shockwave shatters the fuel droplets into a fine mist, speeding up combustion. Scramjets cannot fly anywhere. They are constrained by a narrow hypersonic flight corridor. Flying too low melts the airframe, while flying too high suffocates the engine due to thin air. If a scramjet flies too low, the dense air creates massive drag and extreme friction heat. The airframe glows with orange plasma and can melt under the intense thermal stress. Conversely, if the scramjet flies too high, the air is too thin. the engine cannot scoop up enough oxygen molecules to sustain combustion, causing the engine flame to flicker and go out. This limits air-breathing scramjets to a ceiling of approximately 140,000 feet. Beyond this boundary, the air is too thin, and vehicles must switch to rocket engines. Scramjets also have a low speed limit, below Mach 5. The incoming air is not moving fast enough to compress itself. Scramjets must be boosted to Mach 5 by rocket before starting. Above Mach 15, the internal air temperature exceeds 3000 Kelvin, causing oxygen and nitrogen molecules to split apart. This dissociation absorbs energy, causing the engine to lose thrust. The materials used in scramjets have strict limits. Carbon-carbon composites fail above 2300 Kelvin, meaning the engine walls will melt without an active cooling system. To prevent melting, scramjets use regenerative cooling. Cold fuel is piped through the walls of the engine before injection, acting as a coolant and preheating the fuel for easier combustion. Hypersonic development is incredibly expensive. A single experimental scramjet test flight can cost between $100,000 and $1,250,000 because the prototype vehicles are completely expended. The materials themselves are costly. Advanced ceramic matrix composites that can withstand extreme heat cost over $0.00 per pound to manufacture, driving up production budgets. Scramjets also require special endothermic fuels that absorb heat by chemically cracking before combustion. These synthetic fuels are expensive, costing over $1,000 per gallon. Scramjets represent the ultimate challenge of fluid dynamics, turning supersonic shockwaves into thrust. Thank you for watching Layman's Field. We hope to keep bringing knowledge for everyone.